Hello and welcome back. Today I want to talk about small loop antennas by looking at what makes such a structure special and what are some of the results you can obtain using these. I will be focusing mainly on the electrically small, untuned version of this antenna and its use for the reception of signals. So if you're curious, then keep watching. So a loop antenna is, well, a piece of wire in the form of a loop. While the most common implementation is a circle, you will find variations where either a rectangle or a triangle is used. However, the main reason for going for the circle is that the amount of signal the antenna picks up is proportional to its area. And for a given length of wire, the circle will be the geometric shape with the largest area. To better see what we can expect from this antenna, let's look at it in the antenna simulator. So regardless of shape, so even for this square, from a radiation point of view, a small loop antenna has the maximum radiation in the same plane as the loop itself, and while the field has nulls in the direction perpendicular to the loop's plane. So for this reason, such antennas are also used for direction finding. Anyway, from a polarization point of view, with the loop placed in a horizontal plane, the radiation is also horizontally polarized. So this is a linearly polarized antenna. Now, it is a common implementation to build this as a single turn, but especially when trying to receive signals on the lower end of the frequency spectrum, multi-turn implementations will be used. Even though this substantially increases the signal picked up, it has downsides like added capacitance, which limits the high frequency behavior. Anyway, while this is an antenna used for picking up electromagnetic waves, the small loop mainly responds to the magnetic field component. This is why you will also find the term magnetic loop antenna being used to describe the structure. On the subject of implementations, while you have the single-turn loop and multi-turn loop, another way to increase the amount of signal being picked up is by using a stick of ferrite. This is still a magnetic loop antenna since it picks up the magnetic part of the wave, but with this modification, the voltage generated is also proportional to the ferrite stick's magnetic permeability, which greatly increases its effectiveness. This, however, is limited by the frequency up to which a ferrite will work, so this implementation is only used up to a few megahertz tops. The thing that made such antennas most interesting to me, however, was the electrically small characteristic. You can make these a fraction of the wavelength you wish to pick up, and it still works quite well. Though this mainly applies to the HF bands and below. So one of the graphs you will find in multiple publications is this one related to atmospheric noise. In a nutshell, what this graph illustrates is the intensity of background noise in reference to the thermal noise limit based on the frequency and how quiet the environment is. So the zero trace would be measured in the middle of nowhere when the atmosphere is also quiet, and then at the other extreme, 80, would be in the middle of a city or somewhere where there are intense disturbances present in the area. Now, the significance of this is that it highlights that even if you make an ultra-low noise antenna and amplifier assembly, it does not matter so much since the environment is quite noisy to begin with. In other words, you can use a relatively inefficient antenna, amplify the signal a lot with not a very special amplifier, and you can still get the same results since the limiting factor will usually be the background noise and not the equipment noise. This is especially true below a few hundred kilohertz, then at around 10 megahertz, but it's no longer that problematic above, say, 30-40 megahertz. Now, I've been fascinated by and used these antennas for quite some time now. One of my longest running experiments, observing the change in propagation conditions in the HF bands, was built around a loop antenna. But I also built a vacuum tube amplified version and loop stink antennas. And at the same time, not all experiments were successful. This specific design ended up being quite a successful oscillator. So let's now look at some of the main specifics that such an antenna needs to actually work correctly. Now, the loop antenna used for reception isn't just the loop. There are a few more elements involved. While neither are mandatory, each has their benefits. So the first thing to address is that the loop antenna should pick up the far field signal's magnetic component. But you do not want to pick up local electric fields, which are mainly generated by local noise sources. So the first element to consider is a shield going around the loop. In practice, you can build your loop either from a single conductor or from a shielded conductor, like a coax cable. But keep in mind, the shield needs to be interrupted. So building a loop antenna from these two structures results in more or less the same area, so they should pick up the same amount of signal. However, if we look at the signal that's actually being picked up, with the wire, well, there are a lot of things going on, but crucially, the noise floor is really high. However, with the shielded loop, while the signal itself isn't any better, the noise is. So you can get better signal-to-noise ratios, especially in noisy environments like inside buildings. The next element to mention is that the loop is a balanced structure, while most reception equipment is unbalanced. So some sort of balun is recommended in the chain. It can be right at the beginning or somewhere else down the line. Usually in my designs, I use a 1-to-1 current balun, and I prepared these two boards, once with and once without the balun, to test out. So if we look at these two boards, using the same coax cable loop, well, there is no clear difference. I mean, I used the board that has just or doesn't have the balun, but no other filters or amplifiers were included. And with the setup at least, the benefits are not really clear. Anyway, with or without the balun, usually the impact should be in the range of 1 to 2 decibels, which is of course not negligible, but it's also not always that obvious. Now, the main use case for small loop antennas is picking up the HF bands, but the antenna does not really care about what you want, so it will pick up all sorts of things. And since the pickup efficiency is proportional to frequency, the antenna will pick up higher frequency signals with larger intensity. This is something you don't really want. It's really easy to overdrive a receiver input with strong out-of-band signals, mainly the FM band. So commonly, you can consider a low-pass filter to reject the FM band, or even a band-pass filter to also reject the AM bands. These two being the strongest signals that you will commonly encounter. So if we hook up the unfiltered antenna to a spectrum analyzer to see a wide frequency range, well, the antenna is picking up all sorts of things, from the AM band through the HF bands, FM, and so on. And while the HF bands are some of the weakest signals in there. Adding in filters will not improve on these, but they will help any amplifier or receiver be able to better work without distortion or without being overdriven by the unwanted signals. Finally, the signal the antenna picks up is relatively small, so amplification is commonly needed. One important characteristic of the HF bands is that the ambient noise is quite high, so even if the antenna itself is not all that efficient, you can still amplify the signal quite a bit before seeing the amplifier's noise. And well, these are the main elements of an active loop antenna. This is not the only way in which these modules can be interconnected, but you will commonly see these blocks under one form or another in any active loop antenna implementation. So this is the structure of most loop antennas I built. The antenna itself is some sort of coax, terminated with B and C connectors. At one end there is a connection piece to ensure the shield is split, and at the other is the active amplifier box. I played around with multiple coax impedances, and one note is that the lower the coax impedance, the higher its capacitance. So a loop built from 50 ohm coax has almost double the capacitance of a 93 ohm coax. So the latter should allow operation at higher frequencies. Anyway, the actual antenna amplifier is a board with matching B and C connectors. This should be built inside of a box to protect the electronics. And finally, this is connected through another line 50 ohms this time to a 50 ohm receiver. I commonly use an SDR, so I either use the built-in bias T or add one as an extra element at the receiver side. This allows me to supply the amplifier. Now, one of the latest designs I worked on is this thing. So, starting from the top side, we have the two BNC connectors which go to the antenna, and then from these, the signal is passed through the current balun. Now, here I have two components, just have multiple footprint options, but only one will be actually assembled. After this, I added a couple back-to-back diodes, and the reason for this is to protect the rest of the circuit from electrostatic discharges or any other extreme noise that might be present. Anyway, after this, the signal goes through a high-order low-pass filter, and here I'm not really sure if such a complex filter is really needed, but I guess this is a good topic to experiment with. Anyway, for the actual amplifier, I've tried using these Gali type of gain blocks, like the S66 version. So this is a very simple 3-terminal component, though it's quite voltage sensitive. So that's why the rest of this circuitry is here. Anyway, this is then connected to the last BNC connector, where the feed line is present. So this is also where the supply comes from. So here, just to indicate that everything is working, I also did in an LED to indicate the presence of the supply. With everything set up, we can now hook it up to an SDR. Nothing really fancy is needed. You can have hours of fun sweeping over the HF bands with any receiver you can find on the market. And this is what really made this type of antenna special, for me at least. The performance you get for the size. I mean, using a less than 1 meter diameter loop on the inside of a reinforced concrete building surrounded by all sorts of noise emitters, I can still hear the entire HF band quite clearly. It's not a perfect reception device, but given the restrictions of space, you can't really do much better than this. Plus, it's not all that complicated to build yourself. On that note, I do want to highlight the very first such antenna I worked on. So this started off as a blank aluminium box that I drilled and added the BNC connectors into, and then, one by one, added in the pieces to create a better and better antenna. I started with just a direct connection, then added the balun, the filter, and finally the amplifier board. Going through this step by step was quite a rewarding process, since every element improved on the reception a bit. If I would have started off with a really complicated design, which does not even work because of some mistakes somewhere, well, that would have been really demotivating. But going through the steps one at a time was quite a lot of fun and highlighted what works and what doesn't. In the end, if you're interested in picking up the HF band, I highly recommend trying to build such an antenna. It can be built both as a simple or as a complicated structure, but regardless, most implementations will work to some extent at least. Also, keeping it untuned means it's equally bad, or well good, at any frequency. If only you could build such an antenna for transmission purposes. Well, that's a topic to analyze next time. But until then, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.